My name is Joel Hom. I'm a senior engineer with Contact Engineered Services. My duties primarily is working with our bridge consultants, helping to develop buried bridge projects. That process often also involves interacting directly with various agencies, engineers, and contractors during different parts of a project. We can get involved at any point from the beginning stages of conceiving a project to looking at alternative solutions and even value engineering. And then even during construction, I'll sometimes get involved with questions or issues that come up there. I'm also involved with various ASTM, ASHTO, TRB, Short Span Steel Bridge Alliance, and other organizations on development and improvement of various standards relating to buried bridges. Oftentimes reviewing research papers and providing some input, and also educational training opportunities, either through our bridge consultants or through some of these different agencies. I'm also the current chair of the TRB AKB 70 subcommittee on buried bridges, which covers all types of buried bridges. I'm a licensed professional engineer in 27 states and reside in Hastings, Minnesota with my wife and between 1 and 5 children, depending on the time of year and who's in school or visiting or whatever. So I'm going to talk about this project in Lawrence County, Missouri. This was a DOT project, but certainly everything that we did on here is applicable for more public works type projects and different types of settings. But it's a pretty good example of something that's becoming a little bit more common. This project was part of a larger Missouri DOT design build project that involved the replacement of 19 bridges over a 29-mile stretch of I-44 between Joplin and Springfield, Missouri. The Route 96 and County Road 1147 projects involved replacing 4 of those bridges with a single buried bridge at each location. This project was developed through the design build process with the design build team consisting of Emery Sapp and Sons as the contractor and a partnership of the Lockmuller Group and Parsons Engineering as the engineer. So the design build process it's a pretty collaborative process, and with a lot of back and forth with the design team to find the best solution as we go. It's a very effective approach for developing buried bridge projects because we can get real-time input from the engineer on how the structure meets the project requirements, while getting input from the contractor on how design decisions affect overall costs. In terms of getting the bang for your buck, that's really the optimum approach to take. A lot of agencies and a lot of states don't really have that as an option. The next best thing to that would be maybe working on a performance specification, which allows that type of flexibility to happen somewhat during the bidding process, so that you can really get dialed in on what you're doing. On this project, efficiency was the goal, was a primary goal, speed of construction and minimizing traffic disruption. There's a lot of traffic on this roadway, and one of the things they want to do is avoid road closures and things like that. And also cost ended up being a factor, the initial cost as well as long-term costs. They started looking at concrete girders and other types of traditional, even rolled girder type of bridges. But in the end, buried bridges ended up being the best option. The primary reasons there was the speed of construction. Really, all buried bridge projects are accelerated construction projects. We had the ability and a lot of flexibility to do stage construction and eliminate any kind of a detour. And then also along with that, there was much lower long-term maintenance costs. These structures at the road level, the maintenance consists of maintaining the pavement. Whereas with any other type of bridge, you're talking about bridge techs and joints and bearings and things like that. So that was a big selling point to the DOT with allowing this as a solution. And then there was also a lower initial cost compared to all the other options. So this really checked all the boxes they needed to be checked at each type of consideration. So that this illustrates part of the process of finding the best geometries. The Route 96 structure on the left here needed to be a box geometry because it had to be sized to fit around a certain clearance box for the traffic going through it. And then we were also limited by the existing bridge structure. I guess I didn't mention before that both of these were constructed underneath the existing bridges while they were in service. So these are fully assembled without taking traffic off the existing bridges at all. So with that being the case, that really drove the geometry for both of these. So there weren't a lot of options with the Route 96 structure. With the County Road 1147 structure, there was a lot more height to work with. So we could look at different arch shapes and box shapes. The main differences there are that ASHTO has different backfill zone requirement limitations for boxes compared to arches. So the arch shape is going to be a more efficient shape, but it requires a wider backfill zone, while the box doesn't have quite as wide of a zone, but it's got a less efficient shape, so that might be a thicker steel gauge. So during that process, we're evaluating, does it make more sense to spend a little bit more on the structure and less on the backfill, or the other way around? This process, these are all designed and developed using finite element analysis, so this process is pretty easy to do. When you hear about custom geometries, a lot of times that people envision that means it costs more. In this case, it's the opposite. Doing custom geometries on these types of projects always saves money. So these are the final geometries we ended up with. The Route 96 structure on the left, we had a box culvert structure that was about a 40.5-foot span, fit around the clearance box and fit underneath the bridge. And then the County Road 1147 structure ended up being a dual radius arch structure. Both of these were set on stem walls, in part to better accommodate drainage through the structures. There were some drainage ditches that they had outside the roadway. And this also raises it a little bit to avoid or to simplify maintenance and cleaning with regard to some of the de-icing salts that would accumulate over the winter months. So this is a view of the Route 96 structure. Route 96 was an entrance ramp onto I-44. It passed underneath both bridges at a skewed angle. So one thing that's common with these structures is each individual ring is either 30 inches or 45 inches wide, and the design really works if the ring is complete. If those rings are cut, then you're interrupting the flow of the forces, and a lot of times there's a need to, especially on a skew, you need to reinforce that. Usually with these size structures, it would usually be a concrete head wall. So there was a desire to not have to do that because it would slow down construction and add cost. So we ended up sort of creating a kind of a fake skew on the structure by using an unbalanced step bevel. So the step bevel, what we mean by the step bevel is you start at the crown of the structure, you step down a couple of feet, and then you just cut a bevel in some of the plates at maybe a 2-to-1 or 3-to-1 angle, and then there's usually a step at the end of that. And by doing that, you can accommodate fill slopes. So you can cut those at any angle to accommodate these fill slopes, and you don't have to do it on the other side. So in this case, they opted to do the unbalanced step bevel, saved a lot of cost and time associated with a concrete head wall. It made maintenance of the existing grade slopes easier. They could just do what they were normally doing for mowing on those slopes. And that also gave them the flexibility to expand these in the future if needed. All you have to do is take off that bevel, and you can continue building on more structure if there's a need to widen lanes in the future. The County Road 1147 structure was more square with the roadway. So in that case, we just did a straight step bevel with the bevels on both sides. They were able to maintain the same fill slopes that they had on the rest of the highway. So from a maintenance standpoint, nothing really had to change there. So both of these, I mentioned before, both of these structures were assembled with the existing bridges in place. The way that normally starts is you'll build a couple of rings and then you'll set it on the foundation, and then you just do ring by ring or plate by plate from there. On the Route 96 structure, we thought that there were going to be some pretty tight site constraints with getting underneath the existing bridges. So we initially planned to build a good length of the structure outside of the bridge and then pull it into place on the footing underneath. But as they started, they realized that they had enough room to get that done. So following through the pictures here, starting at the top left, this is at the beginning stages of assembly. These next two kind of show how it was fitting underneath the existing bridges as they went through. These two on the bottom, you kind of get an idea of what the grade looked like on that the unbalanced step L for the skews. The yellow you see here is an HDPE membrane that was placed around the structure to intercept de-icing salts to help with the service life of the structure, and that also minimizes the infiltration of water through bolt holes and seams in the structure that can, during the really cold winter months, can sometimes become an issue. It's become a pretty common approach with these types of structures. You can use it either by wrapping the structure, or a lot of times it's just inserted within the backfill as sort of an umbrella that just basically intercepts surface water and makes it harder for it to get to the structure. Similar process for the County Road 1147 structure. This one was much easier to assemble. This was 5 plates per ring, so to save time, the contractor pre-assembled the 3 crown plates off to the side so that they could bring them in and basically bolt them on as a single plate. But this one had a lot more room to work with. Assembly went very fast. One feature with these types of bridge replacements is that you really don't have to get rid of any of the only bridge elements you get rid of when it's done is just the bridge itself. The superstructure can remain in place, or it can be removed. It's really up to what the owner wants. In most cases, it's by the time you take out the existing bridge, you've got the bridge piers buried quite a bit, so there's no harm in leaving them in there. I think of it as sort of a high strength backfill. So there, after the project was finished, I went to the contractor and to the engineer to get some feedback on kind of their thought process as they were considering options, and their final thoughts on how things went and where those benefits were. So I had mentioned before that the installed cost and time were, those were the main things that the contractor contributed. So in general, they figure they saved about 3 months on the project in terms of the construction speed, and about $500,000. At least that's what the contractor told me. That savings is, that's something I like to keep close to their vest. There were definitely some foundation cost savings. Both of these were on spread footings. With more of a traditional bridge option, they would have been on deep foundations. And then there's always a reduction of long-term maintenance costs. In terms of structure selection from the engineer, they were looking at weight versus span capabilities, the room to construct beneath the existing bridges. This was really the easiest approach there. The similar things that the contractor had to say. There were some safety benefits as well, because there was never any head-to-head traffic during construction. A lot of times you would take all of the traffic from one of the bridges and move it on one lane in each direction on the other one as you're replacing those. In this case, they didn't really need to do that. So the main takeaway, some of the takeaways is in terms of economy. It's a lighter superstructure, lighter equipment to build, smaller foundations. From a construction standpoint, these are modular and simple. They're accelerated bridge construction structures. No specialty contractors were needed or used. A lot of county crews have been able to build these types of structures, earthwork contractors with a little bit of training. So wherever the assembler is at or the contractor is at, we can provide the training they need to get it. And then finally, from a environmental resilience standpoint, steel is a recycled and a recyclable material. the plates used for this are generally minimum 90% recycled content and can be recycled into other bridges later. These are flexible structures. There's a high level of redundancy in the design, as well as the engineering backfill, that all significantly enhances the resilience. And that could be a subject for a future webinar topic, and I think. The reduced carbon footprint from the materials, fewer loads for shipping. These structures you can ship 50 foot of structure length or bridge width on a single truck in a lot of cases, and certainly lighter equipment for assembly. Those are all important factors, especially with some of the requirements with the new transportation bill, talking about the environmental and the resilience requirements there. So thanks for tuning in, and I guess I'll just leave you with a deep thought there.